Welcome one, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing change that. It is Wednesday, our second saddest day of the week. Tomorrow is lab. It's going to be a dry lab. Again, special relativity. The problem is relativistic effects, by and large, are tough to note until you're talking about very, very high speeds. And so we don't have the ability to take you on a field trip at a fair fraction of the speed of light. And so instead what we're going to do is we're going to kind of do a communal worksheet tomorrow. So that is our special relativity activity for tomorrow. The following lab will be an actual get your hands dirty sort of lab. It's actually the one that Einstein wins the Nobel Prize for, the photoelectric effect. But tomorrow's lab will be fun also.
That lab is for tomorrow.
Photoelectric effect is the following week. The syllabus is off.
Oh,
so
okay.
So the lab in between is our special relativity workshop. So
Okay.
Are we still up there tomorrow?
we're still upstairs tomorrow, yeah. So
You said Jeff was going to set up a demonstration for us tomorrow as well. Is he still going to do that?
do you remember which demo this is?
We were talking about it on Tuesday, or on Monday during class. I wrote it down in my notes. Yeah.
Okay. You give it some thought, but remind me at the end of class, and hopefully I will be with it enough that I'll remember what we're doing.
Okay.
But yes, we can do it if we if we set this up with enough time. So okay, so last time we were talking about Einstein's Gedanken experiment, the light clock. Yeah, I think that's where we left off. So let's see if we can. So there's some light source. And then we had, at least according to Einstein, the light goes up, the light comes back down. That's one tick of the clock. We said that this thing was, Einstein is going to patent this at 93,000 miles tall. Why 93,000 miles tall?
Because the light is 186.
Because the speed of light is 186,000 miles per second. Yay? And so Einstein, very, very proud of this clock, as he should be, decides to take it on tour. The problem being that he's going to charge, what did we say, a dime? And I can't afford that, so
It just went up.
I'm a public school teacher. Inflation, sir.
Inflation kick in. So
This is-
it went up.
Much. You cannot afford. You cannot afford a dime. Oh my god.
I'm a public school teacher. Doesn't seem like it's the right distance, but.
Wait,
So-
one dime is less than 1 cent, right? Exactly.
A dime is 10 cents.
Oh, okay, thank you. Because I didn't learn this in my mini school.
according to me, right, so according to Einstein, if this is h tall, then delta t Einstein is 2h over c. In this case, if h is 93,000 miles, 93,000 times 2, 186,000 miles divided by 186,000 miles per second is 1 second. Yay? But for me, we were saying that we can form a right triangle here, right, to figure out what the hypotenuse is, and then we can effectively double this. Another approach is to say that C delta T mark over 2 squared Pythagorean theorem, the base of this V delta T over 2 squared plus the height of this thing, and the height of this thing is still h. That doesn't change according to Mark, right? Does that make sense? So really this is just saying that if the total time is the there and the back, then C delta T mark over 2 squared is equal to V delta T mark over 2 squared plus H squared. Do you guys see that, or? Okay. Do you need me to draw and label the triangle, or are you guys all right with this? So, yay? Okay, so we can fumble around with this if we want, and get that delta T mark winds up being 2h over c over 1 minus v squared over c squared under the radical. Yay? We're happy-ish. Okay. But note that this is delta T Einstein divided by 1 minus v squared over c squared. Yeah? And so, is delta T according to Mark bigger than or smaller than delta T according to Einstein? Well, so V compared to C, V is smaller than C, so V squared over C squared is less than 1. 1 minus something less than 1 is less than 1. Square rooted is still less than 1. Delta T Einstein divided by something less than 1.
Bigger.
So delta T Mark is a longer time interval than delta T Einstein. Yeah?
Yeah.
Does that work?
Yeah.
Okay. So I'm going to be the jerk that I am, and I'm going to say, hey, your clock's broken. I'm not paying a dime to see a broken clock. And Einstein's going to look at his clock, and he's going to see, takes half a second to go up, half a second to come back down, and he's going to say, no, my clock's fine. And to prove it to him, I am going to make my own clock. to avoid any copyright issues, my clock is not going to be 93,000 miles tall. Instead, it is going to be 150 million meters tall. And so, I guess now we also need the speed of light in meters per second. What's the speed of light in meters per second? 300 million meters per second. And so, how long is it going to take my clock to tick?
Divide.
1 second.
1 second. Again, why do I get to... why is Einstein using US customary units and I'm using metric units? It's because I'm telling the story. So the question then is, Einstein looks at my clock. I say that Einstein's clock is too slow or too fast? I say it's too slow. What he says is a second is really longer than a second, according to my measurements, right? Does that make sense? So, I say Einstein's clock is slow. What does Einstein say about my clock? I say his clock is too slow.
Yours too fast.
That's why I set it up this way. Let's see what happens. So what does Einstein say? Is my clock sitting still? What does he see? If I say he and his clock are moving to the right with speed v, what does Einstein see for me and my clock?
So to the left, negative.
Yeah? And so, what path does Einstein see for the light pulse? Well, he sees it do this, right? What does Einstein see? If I say that this takes 1 second, and we both agree on the speed of light, what does Einstein say about my clock?
Too slow.
Also too slow. We both see the other person's clock is too slow. Who's right, me or Einstein?
Both are right.
Thanks, guys. No one ever picks me. I don't know why. Yeah, we're neither of us is wrong, right? This is a reference frame statement. So there's this old heuristic, right? No one has ever said this to you. You guys are all amazingly wonderful people, but because you're amazingly wonderful people, I'm sure you've counseled a friend through a breakup. There's this expression that commonly gets thrown around. It's not you, it's me, right? Physicists, we aren't renowned for our tact or diplomacy. We're more blunt. It's not me, it's you. Of all the people in the world that I could spend time with, I choose one of those other people, right? So here, when we're doing these relativity problems, I want you to kind of keep that in mind. Your measurements are fine, right? It's the other measurements. It's not that there's anything wrong with those measurements, right? They're just not your measurements. Yeah? So here, this is our first chance at introducing a special case. And so you can probably gather from this that there are many, many, many different acceptable values for how long it takes this clock to tick, right? Note that it depends on how fast that frame is moving relative to you, yeah? And so, by the way, I also want to point out that this isn't a parlor trick. This isn't just true for the clock. It's actually also true for Einstein. Time is passing slower on this frame as measured by someone not in that frame. Right? So, but I want to use this to point out a special case.
So you can dilate time as well.
So time dilation occurs for a frame moving relative to, yes.
Oh.
So I'm going to introduce the so-called proper time, N interval. And this is one of those times where we did an exceptionally bad job of naming things. Because proper has this connotation that it's correct or better, right?
Yeah.
I don't want you to think better. I don't want you to think, perfect. This is I think this comes from a bad translation. So in your math classes, have you ever spoken of eigenvectors?
Yeah.
Yes.
Eigenvalues?
Yes.
We hate it.
So it's a good thing that you've heard of them because we're going to be using them quite a bit over the next several weeks. But eigen, I'd like you to think of this as the eigentime interval. Self or own, oneself or one's own, rather than proper. So that is, I think, would have been a better, we're just calling it the eigentime value because you guys are comfortable with eigenvalues and eigenvectors. But instead, we call this the proper time interval. The proper time interval is measured by, here. Is the time interval between two events as measured by an observer who sees both events occur at the same location. So, first of all, what are the two events that mark the start of our second count and the end of our second count? What are the two events here that we're both Einstein and I are measuring?
When the go up and go down.
When the light leaves the source, and what's the second? That's the first event. What's the second event?
Down.
When it arrives back. Does that make sense? Two events. Leaves and returns. Looking at Einstein's clock, which of them sees both of those? Which of them? Which Einstein or me observes both events occur at the same location?
Einstein.
Einstein does, right? Einstein's looking down at the floor right here in front of him.
Yeah.
He sees the light leave. 1 second later, he sees it come back. Right? In both cases, it's right there. Yeah?
Yeah.
Do I see both events occur at the same location?
No.
So I see them occur at event 1, event 2. Right? So Einstein is measuring this eigentime value, this proper time value. I am not. And so what we're going to say is that delta t by any other frame is delta t proper, or delta t eigen, over 1 minus v squared over c squared. We're also going to define gamma, because this term shows up so many times, Greek letter gamma, is going to be 1 over the square root of 1 minus v squared over c squared. And so we could also just write this as equaling gamma times delta Tp. This is our time dilation relation. That's all right? So I often preface this discussion with one of those end user license agreements, those EULAs, that you check on when you download the latest app onto your phone.
No one reads that.
So here is the physics-y version of this, right? So Einstein gave us, well, his first postulate in describing relativity was that all observers will agree on the laws of physics in inertial reference frames. Okay? By inertial reference frame, I just mean unaccelerated. The reference frame isn't accelerating. General relativity. So special relativity is special because the reference frames, we're not going to let them accelerate. General relativity is more general, right? We're gonna kind of ease up on what the restrictions are. So postulate 1, all observers in inertial reference frames will agree upon the laws of physics. End user license agreement, you guys are all okay with that? Check this box, yeah? All right. The second one, this is the shortest EULA you're going to get, right? 2 of 2, right here. All observers will measure the same value for the speed of light in vacuum. C. That's the second postulate. You can kind of even tuck this in with the first postulate, right? Because last time we were saying Maxwell was able to derive the speed of light in vacuum from the electric field constant and the magnetic field constant, right? So are you guys okay with the second one?
Yep.
So this is kind of one of those Jack and the Beanstalk moments. You guys familiar with this fable? He trades the family cow for some magic beans.
Yeah.
I don't even know it has a cow.
Well, not anymore. He traded it for some beans. So you guys have kind of just made a really big trade. If you guys are willing to accept, so this is the thing why they don't want you to read the end user license agreement, right? You've just given away quite a bit. You just gave away the family cow. So you have agreed that we all are going to accept the speed of light is the speed of light. Yeah? And so what do we get in return for that? Well, we can trust the speed of light, but there's a pretty significant cost to doing this. You just caught one of them. One of them is that we don't necessarily agree on the time between two events, right? That's a little frustrating, right? We'd like to think that there is a time between two events and we're all going to agree on it. Well, not if you want the speed of light to be a fixed value that we're all going to agree on. Non-infinite. But don't worry, it gets worse. So what's the thing that we got in return for our family cow? We have the speed of light, right? That's I hope you like speed of light soup, because that's what we got. So we're going to take our light clock and we're going to turn it sideways.
Microwave.
If you're traveling, by the way, why haven't I ever seen this happen? Believe it or not, I'm a germaphobe. I know that's easy to believe, but believe it or not, like, I'm a germaphobe, but I love public transit. Like, I believe strongly in public transit. The part of public transit that I'm not so keen on is the public, but what are you gonna do? I believe in public transit, so I take the BART train quite a bit. I think a lot of you know this. I haven't sat down on the BART train since the third Sunday in May 2002. So.
Oh,
20
years
What's that?
ago.
I've just been standing in the bar seat.
Yeah, and in fact, not only do I stand on I don't hold the handles.
Do you do the?
Those things are disgusting. Yeah.
You spread your legs and you
Yep,
stand.
like this.
Oh,
Yeah. So
You just wash your clothes after.
cleansed by fire, sir.
Cleanse by fire.
Alcohol works just as good.
Before the BART ride. So how come I've never seen this? How come when I'm standing at MacArthur Station and someone is on the BART train, how come I don't see them like moving in slow motion because time is slow in their frame?
Because it's so
How come I
slow.
don't, if they have a clock on the wall, they don't have clocks on the wall. They should have clocks on the wall on the BART trains. But then you'd know how late the train was. So I love public transit. But
Oh, 4 hours.
how come when I look at the watch of someone on the BART train through the window, I'm odd, I don't know. And I look at my own watch, I don't see a difference in the rate at which the two clocks are ticking.
The velocity is so small.
Yeah, so what happens if, 30 meters per second, that's freeway speed, right?
Yeah.
So 30 meters per second, that's as fast probably as the BART train gets. If I divide that by 300 million meters per second, that's equal to, let's see, 3 times 10 to the 1. That's like 1 times 10 to the minus 7. Yeah?
Yeah.
But then I gotta square it, right? And so gamma at freeway speeds is roughly 1 over 1 minus 1 times 10 to the minus 14, which is, give or take, 1 over the square root of 1 minus wait. I lost count. Which is
Almost 1 minus 0. You don't need to rewrite it.
no, it's like It's that. What's the square root of 0.999999? I lost count again. 9999999.
About one.
It's about 1. And what is the 1 divided by about 1?
1.
It's about 1, right? So if I could see the clock of someone on the BART train while I was, sitting in rush hour traffic on Highway 24, wishing I was on the BART train, except wishing that it was an empty BART train, and I had like an endless supply of hand sanitizer and Clorox wipes.
Wear a hazmat suit.
Or a hazmat suit. What would I, if I were to say, okay, you time 1 minute, I time one minute, we're basically going to say the same thing, right? There's going to be an imperceptible difference. This only matters when you're traveling really, really, really fast, right? Relative to a different observer. Does that make sense? Okay, so now let's turn our clock sideways.
Professor, if this is true, then when do we use relativity for our own benefit as people who travel at way, way less than the speed of light?
You mean in your day-to-day life?
Exactly.
GPS.
So general relativity is going to require GPS is going to require general relativity to work. But special relativity, you want an example of how it's affecting you right now?
Correct.
So, are you allergic to muons?
Not that I know.
Probably not, because it is raining muons on you right now. So, in the upper atmosphere, muons are created through a transition from high energy particles striking nitrogen. So those muons are not stable, and so they should survive for about a microsecond, but high enough up in the, like, I want to say maybe 35,000 meters, I want to say. They shouldn't be able to make it this distance because, well, we can sort of even figure that out, right? If you're traveling at very, very great speeds, and you were to say that distance is speed times time. So if the average lifetime of a muon is about a microsecond, 10 to the minus 6 seconds, then if you were traveling, let's say, half the speed of light, 150 million meters per second, 1.5 times 10 to the 8 meters per second, times 10 to the minus 6 seconds. What is that? You guys have calculators. So it's about 150 meters. Nowhere near enough to get you from 35,000 meters up to here, right?
So what you're saying is that traveling at that speed,
So,
the muon sees only those meters instead of...
well, if you were traveling even half the speed of light, right? But you could only travel from birth to death for a total amount of time of about 1 times 10 to the minus 6 seconds. 1.5 times 10 to the 8 meters per second times, let's go whole hog. Let's say you could travel at the speed of light. Muons have mass, so they don't, but let's say it's really close to the speed of light. Well, I could say 3 times 10 to the 8 times 1 times 10 to the minus 6 seconds. So 3 times 10 to the 8 meters per second times 1 times 10 to the minus 6 seconds. It's 300 meters, right? That's not, that's not far enough. If they were really made about 30,000 meters up, you're nowhere near close to making it to the ground. And yet it's making it to the ground, and it's raining muons on you right now. So how is it doing that? Well, so you already gave away the family cow. You already accepted that we have a speed limit. It's the speed of light, and we all agree on the speed of light. So it's not traveling faster. But note that we don't necessarily agree on time, right? What do I say about the clock on the muon, the muon's watch? What do I say about it? Running fast or running slow?
No.
It's running slow. So that 1 times 10 to the minus 6 seconds is taking a lot longer than 1 times 10 to the minus 6 seconds, if you ask me. And so because of that, it's actually able to travel longer, and it's still managing to rain muons on you. Yay?
Thanks.
Um,
Very interesting.
So time dilation, but it's not just time dilation. You already gave away the ability to have an absolute sense of time, or time intervals at least. And now we're going to turn our light clock sideways. We already called this H, but now I'm going to call it LP. I think that that growing sense of dread you have is warranted. So we have, I'm going to call it equation 1, is this guy, delta T P is going to be 2 times LP over C. If you were riding along with this and watching the light pulse go back and forth, that's the time you would measure, the time interval you would measure. And it's a proper time. Why is it a proper time? What are the two events? Light leaves, light returns. Yeah? And so do you see both of those occur at the same spot? You do, and so that's why it's a proper time interval. That's our first one. Our second one, so now Cranky Mark, right, is out here watching you fly by in your fancy flying clock. Let me write down the time interval that I see, and then let's see if we can justify why that's so. So on the way there, so the light leaves, but then according to me, does this wall stay put? This mirror stay put? What's it do?
It's moving forward.
Goes further away. So I actually see this light pulse travel a little bit more than LP, right? And so I'm going to say L over C minus V plus L over C plus V. On the way back, after it hits this mirror and starts coming backwards, what do I see about this back wall? It's actually approaching the light pulse, yeah? And so this one has a little bit less time to travel. Does that make sense? So do you guys see that on the way there, the denominator is a little bit smaller because the wall's moving away? And on the return, the denominator is a little bit bigger because the wall's actually approaching the light pulse. Okay, so that's our equation 2. And our equation 3, sorry, is this one. Delta T is equal to gamma times delta TP. Yay? We can put these 3 equations together, right? I have a statement for delta TP, I have a statement for delta T, and then I have a statement that combines the 2. And so let's do that. So we get that 2L proper, right, that's delta T. Oh no, that's not. Gamma delta TP. Good gracious, Mark. Let's do this in steps. L over C minus V plus L over C plus V. That's delta T, yeah?
Yeah.
That's equal to gamma times 2LP over C. 10th times the charm, is that is how it goes? So we can multiply, I wish I'd done that on the other side, but we can multiply top and bottom of this one by C plus V and top and bottom of this one by C minus V. And we get that L times C plus V plus L times C minus V over C squared minus V squared. Yeah? And so, what nice thing happens in the numerator of that? I have an
So-
LV term and a minus LV term.
They cancel each other
Cancel
out.
each other.
And so,
You mean only two
Carol Stanton would not appreciate this board work. But I think that winds up being 2LC in the numerator over C squared minus V squared in the denominator. Okay?
Yeah.
Now let's take this lump of stuff and I'm going to multiply across by C, basically cross multiply and say gamma times LP times C squared minus V squared is equal to LC squared.
Yeah.
Did I manage to not screw that up?
Yeah,
First for
correct.
everything?
Yeah, correct.
Okay, so let's now kind of undo what I just did and divide across by C squared. You can see I planned this out nicely. Gamma LP times C squared over C squared is 1 minus V squared over C squared is equal to L.
Yes.
Yay?
Yes.
But what is gamma?
Gamma is 1 over square root 1 minus V squared divided by C squared.
Do you see that this is LP times 1 minus V squared over C squared is equal to L? Yay? But do you also see that this is just LP divided by gamma is equal to L?
Yes.
Yay? So, we have another thing. Not only do we have this time dilation to account for, we also have this length contraction to account for. Yeah, so let's recap what you've won here. What did you guys get out of this deal?
It's nice.
You can trust the speed of light. What has it cost us? Well, It's cost us this notion that there is an absolute time interval between two events that we're all going to agree on. It also is apparently costing us this idea that we're all going to agree on the length of an object, at least along its direction of travel. I want to point out that this only changes the length along the direction of travel. So, by the way, does this make, I guess we should decide who gets to measure the proper length.
Yeah, who measure?
So, looking at our picture, LP is the distance between the front and back wall as measured by the person who sees neither the front nor back wall moving. Does that make sense? So if the thing is stationary with respect to you, then you can measure its proper length. And again, I don't really like this idea